you're faced with this massive, big network of resistances. I hope that you've had a chance to copy it down on your paper. You want a nice clean sheet of paper for this, and preferably put this up high on the sheet of paper. We've got 15 volts supplied, and the horrible examiner, me, has said find all the currents and find all of the voltages. Oh geez, where do you start? Just like a show of hands, like who can imagine their confidence levels being high and raise their hand ever so slowly, I suppose, and say, yes, I think I could answer this question. Oh, okay. One person. Leon, wow, you're going to surprise me. Yeah, Mahmoud, you think you could?
I think, yeah.
Yeah, well look, that's good, because confidence is what this game's all about. Just having a go at it, even if you're not 100% sure, say, well, I think I'd have a go at it, yeah. All right, well look, Simon, where would you start with this problem?
Find resistance total.
I love it, find RT. So Simon says, it's like a game, isn't it? Simon says find R total. All right, I love it. I'll go with that. I'm going to go with purple as well. Aaron, where do you think you'd start with this? I suppose, first of all, do you agree with Simon?
Yes.
Find RT. Okay, that gets a tick. Where would you start?
With R5, 6, 7, as they're in series with R4.
Oh, check it out. I love it. R5, R7 and R6, and they are in series or in parallel with R4? They're in parallel with R4. So like I said, with our coloured pencils or those gel pens, let's put another loop around here in a different colour, and then back to purple. R5 plus R6 plus R7 equals, ooh, that's going to be 200 plus 780 plus 330. Heck, what's that? 900, 1200, 1310? Sometimes I do these quickly and I can be out by 100. Is that the nod of approval? Am I right? Yeah. Okay, just as well. 1310. And we want that in parallel with, and I'll do that in my other colour now. It's the beauty of having this graphics package. 920 ohms. And that's going to give us a new REQ at that point in the circuit of, I'm going to use the old 1 over thing here, so it'll be 1310, not 1300, 1310 function 1 on, add 920 function 1 on equals 1 on 540 ohms. That sort of checks out. It's lower than what we started with. Who agrees with me? Heads down, calculators in hands. That's looking promising. I'm liking what I'm seeing, guys. So now that orange loop, everything in that orange loop is this equivalent resistance 540 ohms. So I'll just wait till you finish writing there, because I feel that now you're keeping, we're in synchronization, you're keeping up with me. Mahmoud,
Yes, sir.
you were feeling pretty confident before when I asked to cautiously raise your hand. Where would you go next?
So this 540 ohms
Yep.
equivalent is parallel with 920.
No.
And
That 920 in parallel with all of those equals 540. So everything in that loop
Yeah.
now is 540.
so now R3 and R8 are series with this R4.
Ah, fantastic. So the 540 you're saying is in series with R3 and R8.
Yeah.
Let's do that first. I like it. So let's put a blue loop around these. So that'll be the blue loop. You'll find I do all sorts of crazy things here when I map this out. You know, blue loop. Here it is. If you haven't got your coloured crayons yet, well, you're just going to have to imagine that you've got colours. That's going to be 540 plus 330 plus 330. So what's that? 600, 1100, 1160, 1200. 1200 ohms, and that's going to be the sum of everything that's in that blue loop. All right, Matthew, where do you think we'd go from here? Not really sure. Alex, can you help him out? Simon, I know you can. You're a giant brain at this stuff. You've really excelled. Leon, where do you think you'd go to from here?
First R2 and
Ye-
R2 and one R2 and 100 R2 and 1200 and RRL.
In parallel?
Yeah.
Leon, I love it. Go to the top of the class again. Leon, you're doing well. So can I put then, look, I'll sort of encapsulate them in a pink loop. Oh, check it out. I love these colours. So we want R2 in parallel with, and I'll go back to the blue pen, that REQ that we had from down here. So that's going to be, back to pink again, 720 in parallel with 1200. And answer in pink. 1 on 720. So 720, 1 on, add 1200, 1 on, equals 1 on. I get 450 ohms. Wrong colour, Greg. Let's stick to the original colours. It's not that important, but 450 ohms just for the to make it uniform. 450 ohms, and that's everything in that pink loop, which is including everything on the right hand side of it as well. Now it comes down to just 450 ohms. Peter, where do you think we'd go to from here?
450 is in series with R1.
Series with R1. Anything else? How about series with R1 and R9? Yeah, good. Good. So let's use that green colour around here. Probably some fluorescent highlighters might be good for this too. This blue loop, green loop, geez, green, blue, colourblind. Green loop, we're going to have R1 plus R9 plus and then back to pink, which was that REQ from here. So it's going to be 150 plus 150 plus 450. So 300, 750 ohms. I say that the whole circuit between points A and B is 750 ohms. Just squeeze this in. I don't normally do that, but we'll squeeze that in there. No, we won't. That looks pretty ugly. That looks pretty ugly because it looks like a sort of a thing. We can squeeze it here. 750 ohms. And that is all of that. 750 ohms. There. Wow. Now what can we do? Aaron?
The I total.
I total. Hey, I'm loving this. It's not that hard when we break it down into steps. IT equals 15 volts divided by 750 ohms. 15 divided by 750 equals 20 milliamps. 20 milliamps. All right, we've worked out the total current, but oh heck, we're only part of the way towards solving everything. I mean, we've done a big step towards the solution, but we now have to work out all the currents and all the voltages. So where do we go to from here? Let me give you a hint. Let me help you. Let me push you in the right direction. I'm going to use an orange pen. If I know the total current, that is the current coming into the circuit at that point, and that is 20 milliamps. What do you think I1 might be? Who thinks it might be 20 milliamps? Every hand should be up. It is, in fact, 20 milliamps because the current coming in flows through that 150 ohms and keeps going. So the total current is the same as I1 in this situation. You know, Kirchhoff taught us that the current going into a circuit is equal to the current coming out of the circuit, providing we haven't lost any current to another circuit along the way. All going well, we haven't drained off any current anywhere else, so therefore the current coming in equals the current coming out, therefore the current I9 is also going to be 20 milliamps. I1 is 20 milliamps, I9 is 20 milliamps. Oh, cool. How cool is that? All right. I'm going to stop what I'm doing here in the video. I'm going to give you some time now to go ahead and see if you can work out how to get the other currents in the circuit. How to get some voltages and how to get some currents, and then we'll regroup and we'll go back to the video later on and finish the solution. It's all happening. Okay, So we're back after a lunch break, and did anybody sit down and try and solve this over lunch? You did? Did you come up with the same answers? Now, since I stopped the video, I did continue on and give you people some hints how to do this. And let me just catch up with that, and then I'll come back to you, Aaron. 20 milliamps comes in, goes through the 150 ohm resistor. 20 milliamps then appears at the entrance to this node. That node represents a branching of currents. Some currents go down here, some currents go there. We have, folks, a current divider situation. So down the bottom of the page in grey, I wrote the equation that we use again. And I used pink for the writing because the loop I'd done in pink, and that loop had an REQ of 450 ohms. So we needed to find the current down through 720 and the current through 330. Case 1, 450 on 720 times the 20 milliamps coming in, 12.5 milliamps. Aaron, did you agree with my calculations there? And case 2, 450 on 1200. Why 1200? Well, because that 330 is not standing alone by itself. It's not just in parallel with R2. That in series with all of that orange loop, in series with that 330, are in fact all in parallel with R2. And all of that stuff there added up to be 1200 ohms. So that's why that 450 over 1200. So 12.5 milliamps comes down there, I wrote it in orange. 7.5 milliamps runs along there, I wrote it in blue. And let's continue. So we have then another node. And I might use this fancy green here. Oh yeah, I can see that on the projector screen. Can certainly see it on my computer screen. 7.5, so some is going to come down here and some is going to come over here. So we need to know what the REQ is for that loop. And see the beauty of doing it in color? REQ 540. So I'm going to probably have to migrate down the page here a little bit. That'll be for our, ooh, that looks pretty horrible writing in that color. I'll do it in dark green. So our new current divider is going to be, and this is the end one, the right hand end one, and this is going to be REQ, I'll do it in orange to match that, 540. Run that down there like that. 540 divided by, and oh geez, we need a case 1, case 2, don't we? Case 1, case 2, because it's going to split two ways here. So 540 divided by 920 ohms. 20 ohms times the current that was coming in, that was 7.5 milliamps. I've got Adobe Premiere happening over here on the side, and it wants to keep saving itself and backing up. I don't blame it. I've actually got a half a project running in that for one reason or another I didn't close. I don't know why. I probably should have to free up some memory, but nevertheless, that's case 1. Case 2, 540 ohms divided by, and this is where things get a little bit trickier, but not too much trickier, because we've got no more parallel branches happening here. We're in the last part of it, so that's just R5 plus R6 plus R7, and that was 1310 ohms here. 1310. That's in purple. Come on, get going. Purple. 1310. 1310 times 7.5 milliamps equals equals. How am I going, Aaron? So far, so good?
Yep.
All right, what did you get for the first one, Aaron?
I got 4.4 milliamps.
4.41, 42, 40. How about we make that a little bit, I'd really like to see where we are there. Are we closer to 4.5 or 4.4? Let's see. 540 divided by 920 times 7.5, because we are playing with pretty small milliamp values. 4.40. Fantastic. 4.40. We'll put the 0 there so we know we're in business. And we could minus that from 7.5 to get the other value, or we can do the maths again. 540 divided by 1310 times 7.5 to get 3.09. I'll run with that. 3.09. Whoops, and better write what these are. They're not apples or bananas, they're milliamps. All right, so I would say we've pretty well now got all of the currents that we need. 4.4 milliamps is for the 920. So this is where things get really tricky. 4.4, I'm just going to squeeze that in. You know what I mean. Going down there through I4. In a exam situation, you'd have a table for this, and I suppose I could have drawn a table up and done this a bit neater. And you'd have to write, you know, what I1 is, what I2 is, what I3 is, what VR1, VR2, VR3. They'd be in a table format where you'd put your answers in. And the examiner, of course, would just put an overlay over the top and say, fantastic, he got them all right, or, oh my, he didn't really know what he was doing. I5, I6 and I7, this is brilliant. If they were worth 1 mark each, just by doing one calculation there, you're going to pick up 3 marks. So that was 4.4, 3.09. 3.09 milliamps is travelling around in this loop here to give us I5, I6 and I7. Now, I want to finish this off a little bit prematurely. I'm not going to go through and work out every single voltage, but I'll show you how to work out a couple. Say we want to work out VR6. Mahmood, can you give me some idea how you might do that?
VR6.
VR6.
It's Se17 multiplied by 3.09.
Wonderful answer. 780 ohms times 3.09. And look, I'm going to have to write milliamps there because you can't just go 3.09 times 780, otherwise you're going to get like 22 volts or something, and it's way wrong. So 3.09 milliamps. A few ways you can put that into your calculator. If you're lazy, you can just go 0.00309, can't you? So I'll do that, 0.00309 times 780. And of course, if you weren't so lazy, you could have gone 3.09 exponent, sign change 3, depending on the calculator that you've got. I've got the really old FX82 today, unfortunately, so that's what I've got to do. Use the sign change button over here. I'm missing my FX901. It's buried on my kitchen table somewhere. So we do that and we get 2.41 volts. 1 volts. And if you continue that process right through here, you see, that's the voltage across, here we are down here. That's the voltage across that resistor. We can multiply that current by that, multiply that current by that. Then I'd have VR5, VR6, VR7. I have the current through R4. So 4.4 milliamps times 920 ohms. I've got the current here, 7.5 milliamps times 330. And once I work out that voltage, hey, guess what? I get the same resistance there, same current, same voltage. So I work that out once, I get 2 answers. I love it. And I think the same thing happens here, doesn't it? Because
So for R4, which
R4,
did you use?
4.4 milliamps, 920 ohms.
Yeah.
It's an individual resistance that we're going across. It's one resistor, one current, because they're branch currents. That's another branch current going through there. They've all got 3.09. That's just the current going through that, so that's 4.4 milliamps. Same over here, there'll be 12.5 milliamps through 720, and 20 milliamps times 150, 20 milliamps times 150. So again, one calculation and you get the voltage, which is the same across each resistor. And if that was a 20-mark question in an exam paper, and you can do all of that, needless to say, you're going to get 20 marks. So I'd say this is definitely worth studying and definitely worth understanding how to do everything to do with this question, because you will get a question like this in your final exam. That's why I'm spending this much time on it.
So can you show exactly where it will be on the site?
Unless there's like a
Week.
I'm going to upload the video that I'm doing now.
Yeah.
So this video will be against week 8, I think it is, on the site. And it will also be in YouTube, of course.
What title?
In the cases or where it's divided?
It will be Kirchhoff's, probably Kirchhoff's revision, or Kirchhoff's revision 1, Kirchhoff's revision 2, because I've already done a couple of these before. Yeah. I've already got notes for a circuit like that in the website. This has just got a different voltage applied to it with the same values, and probably just a slightly different way of doing the video to what I did it once before. All right, any other questions? When you want a voltage through a resistor, just multiply the current going through that resistor by that individual resistance. All right, that'll do for that. And then we can move on, and I have yet another marvellous little quiz for you to have an attempt at doing now that you're getting a bit better at doing these types of circuits.